that's coming through.
Yes, we see it.
Gorgeous. Much better beyond just audio. So as we look at reality capture, we're going to be talking some about the BIMForum's level of acceptance, LOA specification, and how that can relate to reality capture. When we look at, I'd mentioned in the chat window, if you could, go ahead and let us know if your firm is already using it. I see some participants are using it in their firms. So we'll talk a little bit about that towards the end. If you're not familiar with this document, you can go to bimforum.org /reality or ask me for this, for a link to this, and I'll be sure to send it out to you. If you want to, you can send me your contact information as well. When we look at reality capture, I want to mention that the perspective of the specification is brought together both from those in design, in civil engineering, structural engineering, architecture, mechanical engineering, as well as those in construction. And some of the vice chairs on the committee with me would be Alan Sonoha with Turner Construction and Mark Epstein from Sunt Construction, as well as feedback from other national organizations. When we look at the concepts of reality capture, you think of the adage where people would say you have to see it to believe it. And additionally, we've heard measure twice and cut once. And what we're going to see as this technology advances in the built environment is that projects using reality capture are going to continue to expand. The capabilities of reality capture will continue to grow, and the costs of deploying it will continue to decrease. We've, at my firm, been utilizing this technology for over 10 years, and that's been consistent throughout that time period. We leveraged this technology from other industries such as aerospace and manufacturing and began to apply it to the built environment. And we have seen that the capabilities of the tools keep getting more advanced while the cost points for deploying that technology reduce. Today we will be talking a lot about laser scanning. The specification that we're referencing from the BIMForum is reality capture, and that could be a lot of other measurement forms beyond just looking at 3D spatial geometry. So obviously there is the impact of measuring the geometry of an object. You could be measuring its temperature and looking at its thermal gradients. You could also be looking at luminance. Total stations are a form of reality capture. You're taking a point at a time. You have moisture readings, airflow, and so I want us to be thinking in a larger concept when we talk about reality capture. We as engineers have a much broader view of this than, say, architecture or some other disciplines. Additionally, we want to think about large data. Reality capture is literally all around us. Some of you may already know this, but in the NFL, all of the major football stadiums have RFID tracking sensors around the upper decks throughout the stadium. And each player has a minimum of 2 RFID tag locators in their shoulder pads, one on the right, one on the left. Linemen have 3, one down lower in the spine of the pad. It is taking over 180 billion bytes of data, real-time tracking, over 31 stadiums, 2,500 players. And they can not only know the speed of a runner, but the direction that this runner's shoulders are pointed. Each football has 2 of these tags in it. They not only know the velocity of the football, but they can tell you the spin of the football as it's looking at both of those tags inside the football and their spatial position as the football is thrown. And the volume of data is really kind of staggering when you think about it. This is reality capture. And what I would submit to you is that the projects we work on are far more important than a game. And what we're going to see in the built environment are not today, maybe not tomorrow, but these volumes of data sets will be very, very common when we start to think of projects in the built environment, both of what we might call horizontal BIM or civil infrastructure type modeling, as well as the vertical environment of traditional buildings that we might think of. The challenge that we're really going to face is that owners need to be thinking about how they handle these data sets. Design teams need to be thinking about how they interface also with building teams, managing these kind of data sets as we look at it. Thermal and imagery. This is another aspect of reality capture. And one of the things we're going to talk about in the spec of reality capture is this concept of density of measurements. But you could see in definitely industrial industry where this could become important. Sound measurements. This could be very important if you're doing a road expansion near an area where you're considering sound pollution and how you attenuate those kind of conditions. That's reality capture. Obviously, we think from civil and surveying the concepts of spatial reality capture. And this leads us to where we bring in the concepts of density. One of the things that we look at is that I like to use this analogy of spray paint. When we're thinking about our measurements of reality capture, these could be seismicity measurements. How often do I need sensors in taking those measurements? It could be a robotic total station with a single point and shooting those at distinct areas. Okay, those are going to be points in space. It could be laser scanning in the cases, examples I'm about to talk about, where I'm shooting up to 1 million points a second. But the question is, what is the density of measurements I need to achieve the goal? And it's not always good to pile in a lot of additional measurements and create a lot of additional points if the file sizes begin to get large and unwieldy. And so we as teams working with owners need to start having this discussion. What are the right amount of measurements? I have seen some teams try to take laser scanning equipment and create topo surfaces from it. And then what happens is, as they begin to process the data, they start to realize the densities of these point clouds are so thick that they need to do a lot of point reduction to get a 10 network that's even reasonable to work with. The file sizes are really unwieldy. And while they are arguably more precise, I could be the devil's advocate and tell you they're not more accurate. There is this dichotomy and tension between precision and accuracy. So just as if I was spray painting, it wouldn't be a good idea to put on 10 times as much paint as is needed. It would look messy, it would create a mess, and it would be very expensive and wasteful. So just like this spray paint analogy, you don't want less than you need, but you don't want more than you need. And we as professionals need to understand these technologies, understand what reality we are seeking to capture, and going on from there. So as we look at this concept of densities, I want us to think in this case, light ranging and detection, LiDAR type scanners, and they're going to shoot points out. And what you'll have reported from the manufacturer, some manufacturers will report scan time, some will report densities, and they will report a gap spot spacing or a point spacing. Depending on the manufacturer, they're going to dictate how they determine that. In this example, I'm saying assume that the manufacturer told you you have a 25 0.25 inch gap at 30 feet. It's linearly proportional. As you go out to 60 feet, you're going to have a half inch gap. And what I want y'all to be thinking about is that there's not any setting on the equipment that'll tell you this is your density. They'll tell you the point, they will tell you your overall scan resolution, and that's going to tell you how many points it will shoot out in a certain gap at a given distance. If your object is 15 feet away, then your gap spacing would be 1/8 of an inch. If it's 120 feet away, your gap spacing would be 1 inch. It's linearly proportional. So if I'm trying to measure objects that are very far off, I'm going to have to shoot at a much higher density than if those objects are very close. So part of the discernment and the engineering that go into prescribing the correct amount of scanning needed for a given task is really understanding this concepts of density. What I like about the BIMForum's reality capture specification that deals with levels of acceptance is it goes beyond just accuracy. It's not good enough to read out the accuracy of the instrument. You need to start considering the densities. And if I'm trying to document drywall in a building, I might be acceptable to have a 1/4 inch tolerance on each measurement with a density in this example of 80 points per square foot or 1 to 2 points per square inch. This is dealing with the gap sizes. So we need to start talking about how many points we need for a given object depending on how far away it is from the laser scanner. If this was other forms of reality capture, you could see this correlation between the accuracy and the units of measurement and the density of those measurements. And you could see this table would vary a lot. In all the examples from here on, we're going to hone in the discussions on laser scanning, but these concepts would apply to other forms of units of measurement for different types of reality capture. This is an example looking at using aerial drones with photogrammetry that created a point mesh of a contour of a dredge island. And from that mesh, then this was brought in to look at cut and fill type work. So here we're dealing with obviously orders of inches and possibly feet with the tolerances of the device. Other forms of reality capture I'm going to show you here will get down to 1/16 of an inch. So there's not one size fits all. And there's a lot of factors that go into the tolerances. And so we need to start looking at what is the right amount of measurements. In this particular application, the aerial drone created a very dense mesh that had to go through subsequent rounds of mesh thinning, which was deemed acceptable to average out the file size where it was reasonably manageable. I think meshes were opened up to the nearest 3 foot or 1 yard intervals between points. And what you do at that point is you're tracking the volumes as you make adjustments of that mesh, and you really are looking at how much are the volumes changing as you start refining or thinning the mesh on that calculation. So in this particular objective, one of the things we deal with is with photogrammetry, if there's also thick shrubs or other artifacts on the surfaces, that technology can pick up those objects and it will skew the data. So there can be work involved in making discerning decisions about what of that geometry to leave out when it's creating that mesh. These are other examples of reality capture where contractors are using this technology to fly around buildings and sites to monitor progress. Here, using photogrammetry and not laser measurements, the tolerances are much looser. You could be thinking of within feet instead of fractions of an inch type tolerances. I know you can get tolerances tighter with photogrammetry, but there needs to be some special consideration in hardware. But in general, you can think of photogrammetry being a lot looser tolerance than laser scanning. I think that would be a fair way to put it. With each of these, if you're looking at this presentation, you really need to consult the particular manufacturer specifications on the equipment you're using, and also consider every year that this technology is evolving. But with that said, here the aerial reality capture provides you a good understanding of the status of the project, and that was its function. And so here you would really put densities not applicable. You're not very concerned with densities if you're calling out this type of measurements as you go. So as we move forward, we could begin to look at getting into the other extreme. This is part of our forensics group. These are centrifuges, and looking at replacement. This is an industrial application, and here I'm working on 2 to 3 mil tolerances, and that's not millimeter, that's 2 to 3 thousandths of an inch tolerances, and these are setting pins I have in here, and these are not photographs. This is a laser scan point cloud, and this is at a very high density. Taking these, as they're zoomed out, you can tell they're a point cloud, but this is not a photograph. That's just millions of points in color making it out. These are Delrin machined pins we put in. They show up in the laser scans, but they act as a wayfinder in the models where we will auto detect that sphere that's set into the setting pin socket. Those were machined on a lathe to match fit the sockets of the setting pins. Here you would see spheres used for triangulating and auto-detecting separate scans, and checkerboards are placed in the distances that are also used to tie together separate scans. And here on the back side of the centrifuge, you would see other setting pins that are used to show up in the scan data and serve as a location aid. And from these, we would work out the brackets of where we would place these. Moving into industrial applications, here you'd see a combination of a robotic total station and one of the laser scanners used in conjunction with each other. Spheres that are used to pull these scans from different locations together, and the total station, which would be used to shoot in points and shoot faces of structural steel to act as a secondary calibration of the measurements. In this case, this was a rail system used to transport jet engines for testing. And so we were dealing with not only tolerances of the structure, but tolerances of rail alignment as we study those. And the structure overall, we were looking at, in this case, we were doing both reality capture and structural review of the system to accommodate testing of larger jet engines. But these would be rolled on a carrier, just the jet engine itself, into the testing base. As we look at that, you see an overlay and synergy both from modeling, which would be existing in green, new is in red, this would be an apparatus, and then the point cloud is overlaid with it, showing you the existing railways as they spin off the main and into each bay. So you see a combination of dealing with both tolerances, but also we need sufficient densities. We're shooting from the ground very high up. So on this one, we would have had a tighter specification on scan densities. Do the spheres have transmitters? Very good question. The spheres do not. They are a calibrated surface, and what happens is each scan, you'll notice in some of these scan pictures I'm going to show you, you'll see a bald spot in the scan data. This is where it's directly below the tripod, and the scanner will scan everywhere except directly below itself. So it will scan almost 360 degrees. It'll do 280 degrees over the horizon and then 360 around. and it will pick up these spheres. And it takes 3 spheres, 3 points to define a plane. We'd like to have more than 3 spheres in any one scan. So when I move the scanner to a new location, it will pick up the same spheres, and the software will be able to auto-detect those and tie those 2 scans together. If these spheres are on platforms that are vibrating, you will get error in your registration. If a technician accidentally bumps the sphere, you'll get error in your registration. If they're outside and you're in conditions where thermal expansion is a consideration. For example, there's a really long run of the such on a rail line, and we put one of these spheres on the magnetic base. You could conceivably, let's say we were scanning within an area, and 2 of these spheres were each side of an expansion joint. It is conceivable that with thermal expansion, you could start to perceive some error as you're measuring with these equipment. But for the most part, you need to essentially have more than just 3 spheres per common in 2 separate scans, and that's so that you can really start to track errors among them. As we look at another example, I'm going to shift. This was in Houston. The building's a little over 100 years old. On this one, I was requested to do load capacity calculations. It's approximately an 8-story building. And one of the things I'm looking at in this is that the steel columns were built up from plate girders. And then they would have large uneven-legged angles, and the long leg of the angle actually turned into thickened portion of the flange the way it was riveted together. So here I'm looking at much higher densities, very tight tolerances, and it does not need to be over the whole project. I'm really just looking at identifying the column locations and the capacities. So far we've gone through 20 to 30-year-old jet engine repair shop, centrifuges. We've talked about 100-year-old buildings. This is new construction I'm about to show you. This was on a military base, and here it's been about 3 weeks. This is a pile of structural steel columns fabricated and delivered that they cannot erect. These are scan clouds. This is not photographs. And so these are point clouds of the space. Again, this is a point cloud showing the anchor rods. And the green is the auto detection in some extraction software where we're coming up with an as-built of the anchor rods. And so now you start to see the as-built of the anchor rods extracted. And what we did is we calibrated a part library in the software. The software we used at the time of this project was utilized for auto detection of pipes for any mechanical type work. But an anchor rod to the software just looks like a pipe coming out. So we modified the library to look for the diameters that correlated to the anchor rods used on the project. And what this allowed us to do is, looking at the pattern, we would look at the intersection of the crosses of a pair of anchor rods and say, by definition, that would be the center line of the grids. And we located the point cloud into alignment with the grids, and then from there began measuring. And not only are some of the anchor rods off location, but they're also skewed. So it's not enough just to know where the top of the anchor rod is, that it's off center. You really have to know, is it rotated and tilting out of plane and out of alignment, i.e. are the rods not plumb? Because that's going to affect how you remedially modify the base plates. In this case, we did scanning on a Saturday, had information registered, and a layout on Monday morning to review for the client. We also were retained to do the steel detailing modifications. We had remedial base plate templates provided to them by end of day Monday, and they were modifying steel Tuesday and Wednesday of that week. They got special permission from the owner to use plasma cutting on site. They'd previously, by contract, not been allowed to use torching on site. But it took steel columns that had been sitting idle for 3 weeks, and they were looking and having to ship all of these columns back to about the fabrication shop about 6 hours drive away. And reality capture allowed them, one, to understand what the problem was, communicate it to the owner. Some of these locations were not only were anchor rods out of alignment, they were simply missing. They failed to install some of the anchor rods. So there was about 80% of the columns within 2 business days of scanning that they were able to begin erecting again. But part of that was due to the fact they understood the existing conditions. When I say existing, the conditions as they were at the end of the concrete pour on this new construction. Other forms of new construction that get into as-builting are post-tensioning. This is a project in El Paso, and this is a few years back. This is probably now 6 or 7 years ago. I believe it to be one of the first post-tension laser scans in the US. Our team was doing this on, this is an elevated garage deck, and the developer had retail tenants that were coming in, but they hadn't sold out all of the unit spaces. So some of these were high-end cosmetics retail facilities, and the owner knew that they were going to need to core this slab to support some of the tenant finish out of these facilities for electrical, etc. They didn't know what spaces the tenant were going to use. The tenants had not finished their interior design of the layout, and the concrete pours needed to go on. So the owner had us laser scan before each concrete pour, and these we did in color. And this is where the discussion of densities come into play. It's typically up to the day before the pour, ironworkers are setting steel, electricians are laying conduit, they're blowing out the forms, and there's a lot of activities going on. And one of the things I mentioned about, if you're on platforms with vibration, most of the vibrations we encounter, you're going to have horizontal movements locked in because of the concrete columns poured below, which are already in place and cured, and formwork ties back to those. You don't see as much horizontal vibrations as you do vertical vibrations. So what we did on this project is we defined a specification that we would only be focused on reality capture on horizontal slab tendons. We excluded a lot of the girder tendons because as they sweep down, there's not really a good way for the laser scans to pick those up. We did do color, which means these needed to be done during the day. If you're going to do color scanning, that's using a photograph, and it goes into the software and colors those points out in space for most of the technology that you're going to see being used. For those, you have to have ambient light. Most scanners will give you a point cloud monochromatic because there's enough energy in the laser to render those measurements. So you can do laser scanning in complete darkness. But if you want a color scan, you need enough ambient light for it to take the photographs after it scans and use those to color the points. Where that comes into play is you're going to see a lot of noise in this laser scan. That's because this formwork is vibrating. And the amount of noise you see vertically is going to be greater than the noise or fuzz you would see horizontally. Also, most post-tensioning cables are going to be, depending on the manufacturer, yellow, green, red, or blue. So this was why it necessitated the use of color scanning. That helped facilitate making out the tendons versus the rebar. But you can start to see, you can see the bands. What was provided to the owner was a 2D map that showed band locations, and it did not matter to them that vertically there was more tolerance up and down on each tendon, because they were just looking, where do I core vertically through the slab? And we were going to have them stay at least one slab thickness away from the tendons anyways. So the fact that since they were getting a horizontal 2D map, the fact that there was more noise in the measurements going up and down, and what I mean by noise, more variance due to the deck vibrating, was inconsequential in delivering the result they needed. If it was important to articulate the tendon drape for structural calculations, what you would see is creating mounting apparatus that would tie into the rebar verticals, dowels, coming out of the concrete column. The theory is, in that condition, the concrete column is solid and separated, while the forms connect to it. The formwork should not be vibrating the column to the magnitude that the formwork itself is vibrating. And the rebar dowels would be coming up out of the concrete column, and you're going to be seeing dowels such as a number 8 or a number 9 bar very stiff, and that would be a more substantial structural connection for the laser scanning equipment to attach to, but it would separate it from a tripod sitting on that form deck. The other thing you could look at is taking it off of the deck if you had sufficient space along the sides to do those measurements. It all depends on the tolerances you are trying to go for. As we look here, this would move into a landscape project. This particular site, you see the site is projected down below. This was an owner that was building a house, and they wanted all of the trees documented. This was on 15 acres. When I say a house, it's a rather large house. This was really 3 properties. There was one property over on this side, a property here with about a $7 million house and a $12 million house. And they were going to demo all 3 of these, join the 3 properties, and just build one $60 million house. The goal here was they wanted the architecture to be very aggressive in how it morphed into the landscape and the trees around it. So our company was retained to do laser scanning of the 15 acres to document every tree. But they also wanted to know the tree canopies. And so what you would see here is very high density, but we also, just due to the nature of it, we captured at a much higher tolerance than was required, because we were modeling the trees as well and programmatically adding in information on tree growth. This was obtained through the arborist, who was also a consultant on the project. They wanted to look at, once we design the new house, how will it function over the next 20 years with these trees growing? So we got into mapping out root systems. And you could see how they were using, this is not a photograph, this is colored point clouds, but you could see the densities we were going for to make out, anatomically correct modeling of each of the trees and working that in a relationship to the property. And this isn't every day, but about every 1.5 to 2 years, we have a project like this. So we've done a handful of these over the last 10 years. And so these are not typical everyday projects, but you start getting into the discussions of tolerance and densities, what you're trying to achieve. Also, the architect, as they're showing the owners, want to have photorealistic work on these tree images. So you have to also start to look at what time of day are you scanning. You can see in this canopy it's very bright white in some of these areas, darker greens. If you're on a project like this and the owner is asking for consistent coloring, you have to have in your scope that you're probably going to have more days in the field, because if you're scanning at the hottest point of the day when the sun is right above you, you're going to get different coloration than you would in the early morning or late afternoon hours and time of year. So this is another part of the scope that came up. Like I said, not everyday projects. The post-tension cable scanning, arboretum type work are ones we're going to have to deal with time of day when you're doing the scanning. This was a project in San Antonio. Some of you may be familiar with the Tobin Center. This was also a while back. We were in this project retained by Lindbeck in Lindbeck Zachary Venture, and Walter P. Moore was structural engineer on the project. And these just show renderings. This was approximately $135 million new addition. And this would be renderings of what it would look like from the Riverwalk. One of the things we had to work with on civil here was tying in the state plane coordinates and control with the steel fabrication. So here we are at the Tobin Center, and this would be renderings of what we would expect to see with it as it went. And this was really what it looked like. As I drove up to the site, this is what it looked like from the front. And then as I went around, this is what it looked like in the back at the time AECO did its laser scanning here. Job site was rather tame at the time. They were doing some testing for hazardous materials on some of the insulation and piping on the far limit, so they momentarily paused construction. This made it ideal for us to come in and scan in these areas where they didn't need to do testing. And as we looked at this, we had a couple of challenges here. The structural steel we needed to visit on was going to be tying into the existing steel structure, starting at what would be the first floor. There's a basement level below, and this would be a balcony level, and then an upper roof deck. So one of the things we would deal with is setting out targets and setting dimensional control. And these are what the checkerboard targets would look like as they're put here. And one of the questions I'm getting from this is, can you vary the density of the points? And the answer to that is yes, you can set different densities. If you were to do sporting clays and you shot a shotgun, at a certain shell that you put in the shotgun, it's going to shoot out a density pattern. But also you could either get closer to the target or further away from the target and adjust that density as well. And same with spray paint. You could get closer or further away. So one of the ways you adjust density is you determine how far you move away from the object, and then you have some range of settings on the equipment itself where you can tell it to shoot higher density, lower density. Higher density, by adjusting the equipment itself, will take longer, and it's going to give you a much larger file size. And what you might find is you're better off taking more lower density scans closer to the objects you care about. And that could be drastically shorter field time, and more importantly, shorter file size, smaller file size. By minimizing that file size, you're really going to save a lot of time, because for every hour in the field, you might have 1 or 2 hours back at the office on the software tying these scans together. And then you could have more time exporting it, and then it needs to get into the 3D modeling environment for someone to make a 3D model from, if they're going to do that. And so if you have a 15-minute scan, at the very highest densities, that could be a 1-hour scan. It's not always better to just ramp up the scan density in the field. It might be better just to get close to the object with a lower density scan, get the densities you need in that area without really increasing your file size. Because even after you finish all that work, you still got to work with the point cloud, and we're talking about terabytes of data in some projects. Currently, we have been retained for a project with the Department of Transportation where we're scanning millions and millions of square feet of their facilities over 100 sites, over 500 buildings, to create building information models of their existing assets. And we might be looking at well over 100 terabytes of data as we progress. We've done a football stadium in Louisiana that was 2 million square feet, and they're approaching terabytes of data. We did over 1 million square feet in St. Louis for the VA hospital system. That one had 7 terabytes of data. And had we not been mindful of our settings, we could have gone to 10 to 14 terabytes of data. And these took a couple months to process. So you could really extend out your work if you're not careful. As we start to look at these targets and where they're located, you would see documenting what you were doing is important. This is 1928 structure, and you can see riveted columns. Concrete on this, we found some of the concrete columns were as much as 5.5 inches off center of the pedestal below them, which is rather remarkable. If you think about one of these columns taking 5.5 inches of eccentricity into its foundation pedestal and standing proud and tall for almost 100 years, it's really a testimony to the flexibility of structure in this. The concrete work you see down here, you could tell it was rough sawn lumber. You could see all the grain patterns preserved in the concrete over the last 90 close to 100 years. This is the scan cloud from that. I can tell you where every grout joint is. I can tell you where the rough openings are in this. This is the temporary bracing to hold the structure in place as they were adding in the new additions. And I'm reading questions as they roll in here. Does the software render from raster or vector? I'm going to keep this particular presentation software agnostic. There are really about 4 major platforms out there between Faro, Trimble, and Leica and Topcon. What I would point out to you as we look at this discussion is that each of those are going to export out the point file, and they have different ways of rendering that information. The point files can also be made into a mesh, and then often that information is going to go into civil infrastructure software and building design authoring environments. And Bentley and Autodesk and others, Trimble as well, through Tekla, have modeling platforms that will read that information in. And so between those, you're going to see a good variety of how they render that information. Needless to say, the point files are very large file sets. Typically the compressed, when we're modeling for a building, we're going to be dealing in gigs of data, and the raw files and the total file set, would be hundreds of gigs, approaching terabytes, depending on a decent sized project. Here you could see there are bald spots in the scan data because we're basically had access to 3 of the levels, so you see shadows up above. This technology is not X-ray, it cannot see through things. You can see here these circles are where the tripod was placed. And so you're moving the tripod around to get overlap. So that's one tripod location. That's another one. This is another one that got oversprayed from other scans. There was probably a tripod set there. There's probably one set here. You can see the remnants of these kind of bald patches where the tripods were set as you're moving the scanner around. Here you have the line work extracted out from the laser scan, mapping out where the structure is to create an as-built of the structure. So to give you an order of magnitude, this is hundreds of kilobytes. It's CAD work with just line work. Gigabytes on the point cloud. Here I've taken 2 scans and I've left one in green, one in yellow, and that's just to show you how you're coding different angles of the surface as they go through. And here you can see the line work extrapolated from those point clouds, and these are just projections. And that created extrusions to make a 3D solid. When you overlay that 3D solid with the point clouds, you're going to see what we would consider a peppering. The scan cloud's capturing the real variation of the structure. The 3D model is an approximation of it to a given tolerance. That 3D model is very lightweight. This is very easy to use. And it's suitable for coordination of the mechanical, electrical, plumbing. But you could always go back to the point cloud for a feel of what's going on. We talked about the tendons. As we looked at the PT tendon project, kind of going full circle, 100-year-old buildings, brand new construction, you'll see reality capture in all of these places. You can see these circles where tendons were, where tripods were moved along. So this is, the tripod was set here. You can see each tendon, and that gives you a feel for what's going on. These are the spheres that were used to triangulate and lock different scans together. This valley is where one of the girders was. Put this in for fun. This was a client based in Germany that had contacted us, and we were doing, for all their initial deployments in the US, scanning of indoor putting greens. Different application, different tolerances, different resolutions needed. These are putting greens that contour, and they've got pneumatic controls and or electric controls with risers about every foot, and they vary the slopes and contour of the putting green programmatically. And then they have a projector, so currently these are used indoors, and it will project on the path of the ball, and it's for training purposes. Well, they needed to know the contour configurations to put it into their software to work out the algorithms to show this projection paths. This is another application where we're dealing with actually thinning the mesh once we achieve it. But what I'm threw this in here for is just an example of the variety of reality capture and how it is all around you. If you go to a shopping mall, if you go to a sporting event, if you go into a built environment, if you're going down the highway, reality capture is all around us. It's growing. And for us to be competent professional engineers in our profession and really extend what we're capable of, we need to pay attention to reality capture and the corollary of augmented reality, where we're going to start seeing projections of systems and both virtual and augmented reality growing. With that, I would look that reality capture goes very far beyond simple geometric data. A lot of the examples today focused on laser scanning, but as professional engineers, I want us to keep an open mind. This is seismology, it's sound, it's light. Any form of reality capture would fall into this, where we would get in the specifications. Traffic counts is a form of reality capture, and you're going to see a convergence of 3D model geometry what we'd call 4D modeling, where we're working in schedule, and 5D, where we're talking about estimating. And you're going to start seeing an overlap of people talking about reality capture as it looks at these different forms of data that are giving you snapshots of reality. Because some forensics modeling is starting to look at really the cost aspect, and that's one of the realities of the project that are getting tied back to reality capture. So I would pay attention to the BIMForum's reality capture specification. It is meant to lay the groundwork to really have a specification that you could expand as a professional engineer on yours. I really appreciate your time taking out here to visit with us. I really hope to be accessible. If any of you have questions that I have not answered in the chat window through the presentation here, please let me know. And really also like to thank Mike and Andreas for being hosts. And with that, we have probably about 4 or 5 minutes left. Andreas, I wanted to hand it back to you and Mike if there were any closeouts and questions.
Yeah, all right. Thank you, Will. No, very good presentation, very informative. So I do have an open question in the chat that is asked, but I think you talk about this in the presentation already. Okay. So is this does the software render from raster to vector? And if you think you already gave an answer, we can just move
on. The answer is yes. It depends on the software you're using. And that's why I was saying, if that individual could follow up with me and talk to me, there are some companies that use more Bentley software than Autodesk software or Trimble. And I could get, if I do not know the answer, there are others on our task force that would be good to tie in. I think that one we'd really need to get software specific.
Okay. Thank you. And another question, this is my question to you, Will, is the application of this technology for underwater structures. Like I'm thinking the bridge inspections, for example, scour and doing things that you don't see from the surface above, or maybe tracking sedimentation in reservoirs, things like that. Has this been used in that environment?
It has been used in tandem with ultrasound, and there's some interesting work where on the front of a boat they will have laser scanning above the water surface and ultrasound below and capture the two of them in sync. Mm-hmm. And that could actually be an interesting, that could be a part 2 of this, just focusing on that tie-in between above and below water. One of the challenges you have with laser light, obviously, is going through water. You move over to a different technological form of reality capture with the ultrasound. But that is being done with teams. There's some in the Houston area, actually, that excel at that. You could imagine offshore oil rigs as well as an area where that would be of interest.
Okay.
Very good questions.
Very good. All right. So I don't see any more questions in the chat. So I'm going ahead and thank you. Thank you again for.
My pleasure.